1 minus 1 plus 2. And this is plus 1, 1 minus 1, 0. Well, of course, you can take other linear combination, but I took the particular combination. It's nice. It's nice. So it turns out that in fact they do have the same symmetry, and well, except that meanings are different. Here it's a topological U1. So you can turn on, these are the global symmetry, so you can turn on the real mass / Fi parameter. So in this case, there's a real mass. So well, let's call it mu first, real mass for this U1. And you could turn on this Fi parameter, which turns on the real mass for this U1J. And then since there are two symmetries, you can also turn on real mass, say mu and let's use the same argument, mu and J. But I wrote this U1J, but nevertheless, from this viewpoint, this is the manifest symmetry which acts on the fundamental fields, not the topological U1 symmetry. So this is an example where this topological U1 symmetry is mapped to the usual U1 symmetry by the dualization procedure. Yeah, okay, so I could finish there. And then, right, so tomorrow, what I'm going to do is that provide yet one more quantitative evidence for this duality using this partition function, so localized partition function, which is written as a particular mathematical identity, written in terms of a special function known as the quantum diagonal function. And then that fits nicely with the framework of three manifolds, where the same function, quantum logarithm, plays a fundamental role. In fact, that mathematics which appears on both sides is sort of exactly the same. And so you can follow the duality between sort of, well, I don't know how to say, the correspondence between 3D equal 2 series 3 manifold step by step algorithms. And that's actually very different from the sort of AGT story. If you are familiar with AGT, I mean, in fact, the difference is in, well, sorry if you don't know, if you never heard about AGT, but suppose that's a correspondence between 4D equal 2 and U. The point is, and then that leads to some precise mathematical conjecture. So right, so that should be the same as that. But in fact, the expression looks very different. Very different. So in fact, there is an industry of taking the expression and rewrite it in a nice form in such a way to prove that they are the same. And that's then try to identify symmetries, argue for that. So it's a huge industry, and there are many papers on that. So that's the case for this 4D equal 2 confrontation, corresponding to manifold. The situation is drastically different here, where we have the correspondence explicit at each level of the confrontation. So that's the difference. And in fact, another difference is that, well, in this case, right, so there, well, maybe I mentioned tomorrow, but there is a direct derivation of this correspondence using the compactation. Namely, well, we don't know the 60 theory, but we can start with the 5D theory, which is the compactation S1. And then compactify 5D theory on some manifold, say, let's take S3 times 3 manifold. I could take the series, 5D theory, put the theory on the S2 times 3 manifold in a nice way, and just do the localization along the S2 direction, and then find, voila, that there is this Chern-Simons theory, which describes this 3 manifold. So that way, the derivation is already given. So it's not the conjecture, there is a first principle derivation of the correspondence, and it's very clean. And the same has not yet been done for this AGT type correspondence. So in fact, so I think, so in that sense, that's interesting. So of course, there are many interesting structures which are new in 3D series, and also from compactation and five-ring compactation. Despite the fact that you might think the 3 manifold is complicated, but nevertheless, from the viewpoint of checking the correspondence, etc., the 3 manifold seems to go ahead. Well, maybe some people object that as far as that aspect is concerned, 3 manifolds actually is easier than the 2 manifold case, which more people are working on. So let me finish here.
Question. The last step you described, like 5D compatible S2, can you do for non-mobility?
Yeah, yes, that's right. In fact, that's a very interesting point. In fact, I could take any 5D gauge theory, its gauge group SO, SP, EL,
etc. You can do that.
Yeah, and then compactify and verify from that first principle of localization computation that it should describe by complexification of that complexified Chern-Simons for that gauge group.
Right.
So that means that.
So in general, your story can be generalized.
Yeah, I mean, that strongly means that the correspondence should be generalized to arbitrary gauge group. Yeah. That's a very interesting point. And another interesting point is that the direct derivation shows very And all the configuration means that, for example, well, I haven't defined the channel 7s, but channel 7s have a gauge field, and there is a gauge field equal to 0 on zero gauge transfer. That's a trivial solution. But the solution to the classical equation of motion, the Chern-Simons, which is the flat connection. And then, so that's a trivial solution. And in fact, that doesn't have a nice geometrical interpretation. Yeah, and in fact, that's more or less the difference between 3D gravity and 3D Chern-Simons. So A equals 0. So they don't have a nice geometrical interpretation. But nevertheless, that should have some crucial roles to play in 3D equal 2 series. And I think that point has not been clarified yet.
In 3D, now being you got like multiple correction in it, so you should have a corresponding counterpart.
Okay, so yeah, I mean, okay, but that gauge group is the gauge group for this 3D n equal 2 series, right? So which is in principle different from the gauge group for 5D n equal 2.
Right.
So well, yeah, that's right. So there is a separate question. So in fact, all the 3D n equal 2 series, I'm going to talk about the abelian series.
Yes.
But as I alluded to a little bit earlier, so I mean, there are dualities between abelian versus non-abelian series. Okay. So yeah, maybe there could be some nice non-abelian description of this whole story, which happens to have the same partition function. And that's a mathematical. And that's related to the issue of, for example, the n cube of this n5, for example. You could just do the same thing. I want to focus more on, so maybe I'll speak numerous, but I could do the complication of n series, for example. And then in that case, we have this, right, so we have the 3D n equal 2 series we obtain is like abelian series, but roughly the gauge group goes at n cube. So it's strange in the sense that it's abelian, but the number of abelian factor grows like n cube. And that's how we see, roughly speaking, this n cube behavior from this correspondence. But of course, it's natural to imagine that there is a non-abelian description of the same thing, like a Kuiper chain, for example, things like that. So that's another indication that maybe there is another non-abelian description. And it's interesting to find that out.
So for this duality, the x, y, z, and for example, in the original, the moduli, so there's no dimension for parameter there, right?
Well, I mean, right. So let's see. So the parameters are, first of all, the gauge coupling is dimensionful.
Even for the x, I thought there was no gauge field in there.
Oh, okay, sure. So here, right. So except that you can count on the real mass parameters.
Yeah, but in the original of the moduli, there's no dimension for parameter anymore, right? So
well, sorry, original means here.
No, for the x, y, z model.
Here.
Yeah.
Right. So if you turn off that, there are no parameters. Right.
So does that mean that the duality only? But here in the original moduli, I still have the dimension for g. So does that mean that the duality only works in the IR and the original?
Yeah, I think so. And the reason is that, right, so in fact that's the subtle point, but in fact the reason is that, right, so for example, it's known that there is no quantum correction to the Higgs branch matrix, whereas there are quantum corrections. And then these metrics coincide only when you take the limit towards zero.
It's crucial to have this 1 over sigma.
Yeah, that's right. So it's like a Taugnat, so there is a factor 1 over g squared or something like that in this scale factor of the Taugnat, for example. And that coincides only in the strict limit, for example.
Okay, so let's thank Masahito again.
So we will have a lunch like here, but to